Let's begin with some questions of timing. Just a little bit of review. So this is a little bit from nucleophilic substitution. So let's imagine we have some carbon, sp3 hybridized, certainly not square planar, but I haven't bothered to show the tetrahedral geometry here. I just want to very schematically ask you about nucleophilic substitution. So in a nucleophilic substitution, the X group, the leaving group, is replaced by the nucleophile. So not worrying about any stereochemical issues or anything too fancy here. We might write this, okay? So what I would like you to do is just pause the video and then outline for yourself on a piece of paper the distinction between an SN2 mechanism and an SN1 mechanism. So this is meant to be a very fundamental question. So don't worry that you're missing something here. Just review what is the essential difference between SN2 and SN1 in terms of the timing of the events in the mechanism. So press pause and do that. The difference between SN2 and SN1 at its core is that an SN2 mechanism is one step, whereas an SN1 mechanism is at least two steps and has a carbocation intermediate. So overall, the same stuff ends up happening. The leaving group leaves and the nucleophile takes its place, but it's a different order. So let's just do SN2 in the green chalk, and if you didn't do this already, go ahead and do it. In SN2, the nucleophile arrives. So from the back side of the carbon X bond, I know I haven't drawn this out tetrahedrally or anything, so this is a little bit imperfect, but the leaving group leaves, and one step gets you to the substitution product. Okay? If you haven't done it already, pause the video again, switch to a different colored pen or chalk, or use the same color, just use a different page. The SN1 mechanism, how does that go? Well, in SN1, the leaving group leaves first. So this is going to be the SN1 pathway. Once the leaving group leaves, you end up with an intermediate carbocation. The leaving group has departed. Here it is, X minus. And then, and only then, so it's a different sequence of events, first the leaving group leaves, then the nucleophile arrives, and that gets you to the final product. So the key here is you can have the same overall process. Now, it's not going to work as well for certain substrates as others, depending on the particulars of the reaction, but you can have the same type of products that are derived through different mechanisms. So now, as we've started to talk about elimination reactions, let's do something similar in terms of thinking about the possible timing of events. And this is meant to be a little bit of a review of what you know about E1 versus E2 eliminations, and then also building in something a little bit new. So we're just going to move over to the other board. And let's call this not substitution, but eliminations. And as we've seen, timing is also an issue for eliminations in much the same way that it was for substitutions. So let's just have a carbon with the leaving group attached. And which letter of the Greek alphabet do we typically use for the carbon that has the leaving group attached in elimination reactions? Think hard. Alpha, the alpha carbon. So here is the alpha carbon. And then on the carbon next door to the alpha, which as you might imagine we call the beta carbon, on the beta carbon there's going to be a hydrogen. And again, as you've seen in some of the reactions we've worked through in class and on the assignment so far, the exact three-dimensional positioning of the groups, the tetrahedral nature of the alpha carbon and the beta carbon, they're both sp3 hybridized. That's going to matter in some cases, but again, we just want to keep it very schematic like we did for the SN2 versus SN1 timing question. All right, so in an elimination reaction, can you write the products? So remember, or the product in this case. So in an elimination reaction, you're going to lose the elements of leaving group and a proton from the beta position, from the carbon next door. Okay? So in this case, it would be loss of HX. So before we do anything mechanistically speaking, just write down the elimination product from this example shown here. The product of elimination has a carbon-carbon double bond between the alpha and the beta positions. The H has been eliminated, the proton has been eliminated, and the leaving group carried away a pair of electrons, and that has also been eliminated. So you will see that those components are no longer there. And then there are the two other things. I haven't specified what they are, but those two other things on the beta carbon and two more groups left on alpha. Notice I've drawn the alkene with the proper geometry, sp2 hybridization, sp2 hybridization, trigonal planar geometry at each of those positions. All right, so what I would like you to think about now are, and you already have experience with 2 out of the 3, but what I would like you to think about are 3 mechanistic options, and they're just going to differ in the order of events. So just like SN2 and SN1 accomplish the same overall transformation, just in a different order of events, I want you to think about the possibilities for elimination, and you already know 2 of them, or you're familiar with 2 of them. It has to do with the E1 option versus the E2 option, but I'd like to see if you can think of a 3rd possibility as well. So you know you have to break this bond, you have to remove a proton, you know you have to make a double bond between alpha and beta, and you know that the leaving group has to leave. So see if you can think of 3 different ways of doing that that differ just in the order of events. Please press pause, and while you're thinking about that, I'm going to go and erase the other side of the board. All right, let's begin with the first type of elimination mechanism that you learned about. I'll just redraw the starting compound. Very, very good idea to always label your alpha carbon. Just like we did when we did substitution reactions, it was all important to focus on the carbon where the leaving group was attached. That carbon is also very important, obviously, in elimination reactions, so always label it, and then label the beta position as well. So let's start with an E1 type of process. All right, so maybe that will spark your memory if you didn't get this already. What is the first step in E1, and then how does it proceed? The first step in E1 is departure of the leaving group. So first, the leaving group leaves. So that's the timing issue. When the leaving group leaves, you end up with a carbocation. Notice the positive charge is on the carbon where the leaving group used to be. So just be sure you generate the carbocation in the right place. So that's step 1. This looks a lot like SN1, Remember, SN1 and E1 share a common intermediate. This carbocation could go on and do SN1 chemistry, or it could do E1. So we're partway there. The leaving group has left. And then the next step in this process is loss of the proton from beta and flow of those two electrons to make a double bond between alpha and beta. Okay? So in the absence of some solvent or something, what you could use as the base to remove the proton would be the X minus that left in the first step. And so in the final part of E1, you end up with the carbon-carbon double bond between alpha and beta, and then the byproduct is just HX. All right? If you were in a solvent like water or ethanol or methanol, it would make better sense to use the solvent molecule as a base to remove the beta hydrogen. But here is we were focusing on the timing. So the E1 is step 1, leaving group leaves. That gives a carbocation. And then in step 2, you lose H plus from the beta carbon, and you make an alkene. All right? So first the leaving group goes, then the proton is removed, and you make the double bond. Okay? So that is the E1 type of reaction. What about E2? Do you remember what happens in E2? So you can work on it while I copy this structure again. All right. So again, we have the alpha carbon and the beta carbon. So E2, how about E2? How many steps are there in the E2 process? Is it a sequential, step-by-step, couple different steps in a sequence? The E2 reaction is a one-step process, okay? A one-step process where the proton is removed from beta, a double bond forms, and the leaving group gets kicked out, all in one fell swoop. So it's kind of similar to SN2 in the sense that there would be just one transition state in between the starting material and the product. And so for this, I guess I should have stipulated, we've got some kind of base around. So can you push the arrows for an E2 type of elimination? So this is just a different timing. Everything happens all in one smooth process, one transition state. The base starts things off. So remember, relatively strong bases like ethoxide or methoxide or hydroxide would be good for E2. So here comes the base. It removes the proton. Make sure you remove the proton from beta. That frees up these two electrons to do this, make the double bond. And then this is kind of like an SN2 process where formation of a new bond to the carbon that has the leaving group attached forces the leaving group to leave. So in terms of pushing these three arrows, the way that you should push these is you should always begin the arrow pushing from the base, because that's the thing that initiates this three arrow mechanism. Just like in SN2. Remember in SN2 it was always a good idea to start the arrow pushing from the nucleophile. As the nucleophile added to the carbon where the leaving group was attached, the leaving group got expelled. Okay? And so when this occurs, we get the same product that we did up above. There's a double bond between the alpha carbon and the beta carbon, but this is a one step. Another way of saying that is that it's a concerted process. Just one reaction step, one transition state from starting material to product. All right, so the contrast here, E1, so there's just one step down here. E1, leaving group leaves, lose proton from next door. E2, it all happens in one stage. So now we're up to the third one. Can you think of a third one? So E1 was leaving group leaves first, proton gets lost second. So that's my hint. What could the third one be? A different order of events. And while you work on that, I have to erase the other side of the board. E1, first the leaving group left, then we lost the proton. What if we reversed the order of those steps? Instead of having the leaving group leave first and then lose the proton, what if we lost the proton and then had the leaving group leave? So in this scheme, we would also need a base. So here's my base. It doesn't have to be negatively charged, but I could put a negative charge on there. So in the first step, I would lose this proton. The base would come and remove it. And the difference between this and E2 is that instead of using these electrons to make a double bond and kick out the leaving group, I would have a preliminary step in which those electrons are dumped onto the beta carbon. So here is the beta carbon. It now has a pair of electrons on it. The alpha carbon over here is next door. Here's alpha. Here's beta. The base has removed the proton, so I'll draw it up there. And then I have to conserve charge, and if I check the formal charge on this, that's a negative right there. Now I have a full negative charge on the beta carbon. Well, I could use that full negative charge, this pair of electrons, now in a second step to make the double bond and kick out the leaving group, and that would take me to the final product. So in this case, it's step 1, deprotonation at the beta carbon, and step 2 is alkene formation by loss of leaving group. So the two processes are reversed in this particular case. So this type of mechanism is known as an E1 mechanism as well, because it turns out to have unimolecular kinetics. It depends only on the concentration of the substrate. So this first step is typically fast. It's not rate determining. It's this second step that is rate determining in most cases. So this is a unimolecular elimination where this negative charge kicks in and kicks out the leaving group. Sorry, I'm missing an arrow there. But to distinguish this from the other E1 mechanism, we add a little thing like this, CB. This stands for unimolecular elimination via the conjugate base. So first you generate the conjugate base of the original compound, and then you undergo the elimination. All right? So you might ask, what kinds of factors would favor this E1CB mechanism? So maybe you can think about that. What kinds of groups? So let me just use the letter G for a group here. So what kind of group do you think would favor this type of mechanism? And what kind of leaving group also would favor E1CB? So what are the electronic properties of this type of group that would make this initial deprotonation more favorable? Think about that. Well, if you're going to make a full-on carbanion at beta, what you would like to have is this group being electron withdrawing. So if this were some group that could stabilize this negative charge by resonance, for instance, so sometimes we'll abbreviate electron withdrawing groups as EWG, and you might think about, for instance, a carbonyl group would work, or a nitro group would work. So maybe try drawing some structures of that type where you put your favorite electron withdrawing group here and show how this negative charge could be stabilized. And then how about the leaving group properties that might encourage this E1CB type of mechanism to be operative?
You might want a leaving group that's an acceptable leaving group, but not the greatest leaving group. Because if it's a really good leaving group, it might just leave, that's E1. Or it might be relatively easy to push it out in an E2 type of sense. But if your leaving group is not so good, so not such a good leaving group, it might be hard to get that leaving group to leave. So if you build up a full negative charge, so there's a full -1 charge at the beta carbon, now you have a much bigger push to push the leaving group out. So sometimes E1CB is more favorable when you have a not so good leaving group that really requires a full-on negative charge next door to push the leaving group out. So I would like you to just sit back and think about these three elimination mechanisms. E1, E2, those are certainly the two more important ones for our purposes. But there's also this E1CB mechanism, which we will see in various iterations, some this semester and some next semester as well.